Okay. Still working on the testing here. They're the ones that are sitting on my desk right now, though. So, don't have a lot of grading time today, but I'll get them tomorrow probably. Anybody think anything we need to talk about other than section 10.1? Thinking of anything? Okay. Well, as the sign-in sheet comes around, those days that are on the sign-in sheet are all we have left. That'll be our last page. Okay. Some of you might not even have to come for that last day, because that last day will just be final exam review. Get a couple. It's meant to be. You might as well get both of them.
Thank you. Appreciate it.
You're welcome. That's okay. I just go with the crutches. All right. So we don't have all that much left. We have 4 sections out of chapter 10, and then 2 sections out of chapter 12, and that'll be it. Chapter 10 flows in a similar way to the way chapter 8 did, because several of the sections are really similar to each other. So 10.2, 10.3, 10.4 are all similar to each other, doing this thing we're calling hypothesis testing in a similar way to how we had the different types of confidence intervals we did. They were similar. And then 12.1 and 2 really go together. It's really like just one section. Can't think of anything else we need to talk about? Okay. How'd you feel about the test? I didn't get far enough into them yet to have a feel yet. Think it was okay? So? Good? Good? All right. So, sometimes test 1 is tougher for people with all that vocabulary on there. Sometimes test 2 is a little tougher. So I don't have one that I expect to be the hard one in here. Really, it's just different from person to person. So I don't really know. Okay. All right. So chapter 10 is all about this idea of doing what we call a hypothesis test. And confidence intervals are great. I mean, they're really useful. But the main reason why most of you are in here is to get this idea of hypothesis testing. It's good to know the lingo and things like that that go along with statistics, but the reason why most of your majors have picked this class to be a math class that you have to take is because of this idea of hypothesis testing, just so you're exposed a little bit to it. In this section, we're kind of looking at the outline of how hypothesis test works, okay? And then we're going to focus on the very first step and then the very last part of hypothesis test. And then in the other sections in this chapter, we'll fill in the details in the middle. So it's a little weird because we're looking at the beginning and the end, and then we'll talk about the middle later. It works well, though, even though it sounds a little strange. So this idea of hypothesis testing, all we're doing, we are working with it's a formal decision-making process. That's all a hypothesis test is. Okay? It's just a formal decision-making process. And we'll get more into it as we go. Okay. So here's our outline. Okay, you can kind of break it down into 4 steps. Part of this you could switch around, and it really doesn't make a difference. But this is how our textbook lists out the 4 steps. Okay, so today the main thing we're focusing on step 1. Okay? Anytime we do a hypothesis test, we're actually going to have two hypotheses. And the two hypotheses we call the null and alternative hypothesis. And we'll see more about those shortly. Step 2, we kind of get into the nitty-gritty details of our particular question we're trying to answer. So we figure out, do we use a Z distribution or a T distribution, and then do our get things ready. Okay, figure out which formula we're going to use and things like that. And then our textbook throws in state the level of significance. We'll see that in a minute. Really, that can, as long as you get that step done by the end, it's okay. That's where our textbook puts it. Step 3 says gather data. That's where most of the work would come in real life. Okay? So that would take way more time than all the rest of this put together. Gathering the data and then calculate the necessary sample statistics. So for us, gathering our data is just going to be reading the problem. And we're not going to have to collect any data from out in the real world. Okay? But then we will make the calculation. And then step 4, we want to draw a conclusion. We're not even going to touch on that part of step 4 today. The only part of step 4 we're going to look at is interpreting the decision. So our focus, we want to talk about how to start a hypothesis test. What does it look like when we get the two hypotheses? Okay. And then what does it mean when we get a conclusion to a hypothesis test? Those are our two focuses today, and we will also look at a couple of type of errors that can happen. That's the outline for today, and we'll fill in the rest of that in the next section. Okay. All right, so we said we need two hypotheses. So one of them, I almost said the first one, okay, they're not first and second, we have both. Okay, we call the null hypothesis. And you'll see this notation used here in just a minute when we look at our definition slide. Okay, so null is another name for 0. So we have a big H with a subscript 0 on there as our shorthand for the null hypothesis. Okay. And then the other hypothesis we call the alternative hypothesis. And our notation for it, we'll have a capital H with a subscript A, okay, for alternative. Okay. So we'll have H0 and HA, or H sub 0, H sub A. Either way you want to read those, or you could just call them the null and the alternative. Okay. That's what our notation is going to look like. Okay. So let's get a few definitions here. Okay. I will say it's perfectly understandable if a lot of this just sounds just like jargon, okay, today. It takes a little while for what's going on with the hypothesis test to soak in. Okay? So don't panic if you don't feel crystal clear on everything today. The main thing we want to be able to do is get to the point where we can at least practice getting the hypotheses from a problem. And then we want to be able to interpret the result at the end. That's the main thing. So don't panic. Okay. All right, so our first definition, that's just of a hypothesis test. Okay. The definition our textbook gives us is a statistical process for determining the likelihood that a given hypothesis is true. Okay. And again, you can just think about hypothesis testing as a formal decision-making process. So all we're really doing is we are going to go through these steps, and then that will tell us, does it look like this hypothesis, we have evidence for this hypothesis to be true, or does it not look that way? Okay. And we're just being very formal about making that decision. Okay. So then we have our two hypotheses. So here's some more information about those. Okay. So the alternative hypothesis, HA. Okay. Both of these hypotheses are just mathematical statements. So we're making a claim about some type of population parameter. We're saying this parameter is bigger than this number or smaller than this number, something like that. The way things will be worded, the alternative hypothesis is usually the one that the researcher is trying to support. So we're doing research and we're trying to support our alternative hypothesis with our statistical evidence, with our data. So sometimes you'll see the alternative hypothesis called the research hypothesis. All right, and then our null hypothesis, H0, one thing we're told is it expresses a value currently believed to be true. So you can think about the null hypothesis is kind of what you would call the status quo, right? This is kind of like the commonly believed thing. And then the alternative hypothesis would be we're trying to show that it's not the commonly believed thing. We're trying to support the alternative hypothesis. Okay. And one really important thing about the null hypothesis is this last statement. Okay. The null hypothesis it says it will always be a statement of equality. So that means in the null hypothesis, remember it's a mathematical statement, so the null hypothesis will always either have an equal sign or less than or equal to or greater than or equal to. It always has to include equality, okay, in the null hypothesis. Okay. And once you get one of these hypotheses, or once you get one hypothesis, it makes getting the other one easier, okay, because these two are always opposites. I don't know why our text didn't include that here. So if one statement says one thing about a number, then the other hypothesis will be the opposite. And they're always going to be complete mathematical opposites. Okay. Questions on any of that so far? I know it's just a bunch of gibberish at the moment. We're going to practice figuring out what these hypotheses should be. Just a second. Can't think of anything? Okay. All right, so let's look at an example here. So we've got a scenario set up where we would want to do a hypothesis test potentially, and we want to figure out what the null and the alternative hypotheses would be in this situation. Okay. All right, so this one says at Northwest Mississippi Community College, syllabi for online classes state that students should expect to spend 10 hours per week completing coursework for each 3 credit hour class. The director of e-learning for the community college is concerned that students are being required to spend more than 10 hours per week doing work for each 3 credit course. Okay. So our person that would do a hypothesis test in this situation would be the director for e-learning. They're the person that thinks students are having to spend more than 10 hours per week on each course. So the thing that our director of e-learning, our researcher, would be trying to show in this situation is that here it's not clear, but what we're talking about is students are having to spend 10 hours per week on average, right? So we're dealing with a mean. Okay? So the director of e-learning would be testing, okay? See if students are spending an average of more than 10 hours per week on each course. So that would be our alternative hypothesis, and the way we would write that down, usually the alternative is easier to come up with first. Not always, but usually. So here we're dealing with, our numbers we're dealing with are means, and it's going to be population value, so we'll say mu. And then the director of e-learning is concerned that students are having to spend more than 10 hours per week. So our alternative hypothesis would be that mu is greater than 10 hours per week, greater than 10. That would be our alternative hypothesis on this one. So once we have that, it makes getting the other hypothesis easier as long as we remember they have to be opposites. So our alternative hypothesis is that mu is greater than 10. So what would the opposite of that statement be? Yeah, mu is less than 10, but we have one other thing we have to remember with the null hypothesis. It can't just be less than, it has to be less than or equal to 10. We have to have equality included with the null hypothesis. So these would be our two hypotheses on this one. Okay? So the null hypothesis is kind of what we are supposed to believe now, right? So we're supposed to be expecting students spend 10 hours per week for each course, or it could possibly be less than that. But what we would try to show with our data, and what the researcher would try to show, is that they're having to spend more than 10 hours. So these two things are opposite. The idea is that if we were going to go through and do a whole hypothesis test here, the way our formal decision-making process we call hypothesis testing works is we start off, so we're trying to show the mean would be greater than 10 on this one. So what we would do is we start off assuming that the null hypothesis is true. So we would start off assuming that students are spending less than or equal to 10 hours per week on each course. We would collect our data. Okay? We crunch some numbers and turn our data into what we call a test statistic. And then we can look at that test statistic to see if we have evidence that the alternative hypothesis may be true. Okay? If our evidence is strong enough supporting the alternative hypothesis, then we'll say, well, our assumption was probably wrong. Right? So that means this thing's probably true. Okay? It's a roundabout way of getting to a conclusion. Okay? It's similar to what we would call a proof by contradiction in math class. And you start off assuming the opposite of what you want to show. And when you say, well, that must not be right, then that means the thing that you wanted to show must be right. And so we're kind of going around the long way, okay, to get to where we want to be. So it's a little strange there, but that's what we do. So the main idea, okay, here's our hypotheses. Okay. In Hawks, mu's on the keypad, so you can just use the button for mu to fill that in, and then you can need less than or equal or greater than or equal, those are on the keypad too. Use those. And in Hawks, the way you would put your answer in, this would be the answer box. You have two of them. Okay. So you do need to know which one's which. Okay. The one with equality is always going to be the null hypothesis. Questions on that one yet? Yep. Equal will always be in the null hypothesis. With the alternative hypothesis, we can never show something that's equal to some number. Our choices on the alternative hypothesis is that we can show that it's bigger than some number, that it's smaller than some number, or that it's just not some number. Those are our choices, yeah. We'll see one of the other ones on the next one. So, okay. Other questions so far? You might need to see a couple before you kind of get things flowing up there to know what you might need to ask. So. Okay. So let's look at another one. That's what we said. Okay, but I left it in the slides in case you want to read over it. Okay. Here's another one. This one is a little wordy, and believe it or not, I cut out some of it. Okay. right, so this one says a group of students decided to conduct their science fair project around the amount of time an average adult can hold their breath. Part of the group found research to suggest that adults can hold their breath for 30 seconds when submerged in lukewarm water. The other half of the group found evidence to suggest that the mean time is different if the water temperature is colder. The group would like to test this claim about adults holding their breath in cold water. So it's usually always helpful, okay, to start out thinking about what claim whoever's doing the research is trying to test, okay? And this one even kind of spells it out that way for us. So it says the group would like to test this claim about adults holding their breath in cold water. So on this one, we kind of have to work backward to see what that claim was. Okay? So if we work back, okay, the claim about holding breath in cold water was that the mean time is different if someone's holding their breath in cold water. Then we have to go kind of back one more step. Different than what? Different than the 30 seconds it's supposed to be if they're in lukewarm water. Okay? So this one, you kind of have a few steps you have to work backward on. Okay? So the claim in words that we're trying to test is that the mean time adults can hold their breath in cold water is different than the mean time they can hold their breath in lukewarm water. Right? And we have a number for lukewarm water. Right? The number for lukewarm water is 30 seconds. So we could reword that. We could say we want to test whether the mean time is different than 30 seconds when people are holding their breath in cold water. Okay? Now, one thing that makes these a little tricky to start with, and you're used to seeing them, we don't have any hint about whether or not holding your breath in cold water, you're supposed to be able to hold it longer, or if it's supposed to be shorter. Okay? We don't have any kind of indication which direction that it would be. So all we're testing here is if it's different than 30 seconds. It may be longer, it may be shorter. Okay? So our alternative hypothesis, again, we're dealing with means. Okay, so we're going to test to see if our mean is different than 30 seconds. That's what we're trying to test here. So we need some type of mathematical symbol that could just mean different than 30. Anybody got any ideas? This one you don't get to use a lot in math class. Can't use less than, right? Because that would mean it was smaller than 30. You can't use greater than, that would mean it's bigger than 30. We need one that'll go either way. Not equal to, yeah, not equal to. So we're just testing to see if our mean is not equal to 30. Okay? So a little unusual. Again, we don't get to use that symbol much in algebra and things like that. So if we don't have any indication whether or not our number should be more than some number or smaller than some number, we just want to test to see if it's different than some number, then we can use the not equal to symbol. Okay? Because if it's more, it's not equal to. If it's less, it's not equal to. So it works both directions. All right. So that makes this part even easier. What's the opposite of not equal to 30? Equal to 30, yes. So our null hypothesis will be that the mean does equal 30. That would be our two hypotheses. Questions on that one? Need to walk back through part of it? We kind of had to connect several little pieces of information together to get to that alternative because of how it was worded. Okay, on that? Okay. All right. Let's look at another one now. These just take practice. Okay, the more of these you do, the easier and quicker they are to pick out. Okay. Let's look at this one. This one says, a leading news authority claims that the governor's job approval rating has dropped over the past 3 months. Previous polls put the governor's approval rating at 56%. The governor's chief of staff is concerned about this news report since it's an election year. He wants to run a test on the claim. So what claim would the chief of staff be testing here? That the approval rating has dropped. Okay, so we need to come up with a way to put that in mathematical statement form. So what was the approval rating previously? It was 56%. So if it has dropped, that would mean that the approval rating is less than 56%, right? So it was 56%. If it's dropped, that means it has to be less than 56%. Okay. And we only have one other piece of information to think about to get our hypothesis. Here we're not dealing with means. We're dealing with this percentage. Do you remember what we call those? Had to deal with them in 8.4 was our last confidence interval. They were proportions. Proportions where we had P and P hat. So here our alternative, well, I guess I didn't leave myself space there. So our alternative hypothesis, and this time we're not dealing with mu, we're dealing with P for proportion. And we're saying that if it's dropped, that means that now it is less than 65%. So you can write it as a percentage. Sorry, it's so low on the board. Okay. You can just write it as 65%, and that works for the hypotheses. If we were going forward with the hypothesis testing procedure, okay, it's going to be a little more convenient if we wrote it as a decimal instead of a percentage. So percentage is fine, okay, but it's a little bit more convenient if we write it as 0.65, okay, for 65%. Oh, 56, yeah, thank you. Okay, 56. So then if our alternative hypothesis is that P is less than 0.56, what's the opposite of that? Yeah, P is greater than or equal to 0.56. Or again, you can write it 56%, that's fine. Now, I had 65 when I had it a percent too, didn't I? Yeah, so you can write it either way. Decimal is going to be a little convenient down the road, but as far as just getting the hypotheses correct, you can write it either form. Hey, Hawks will take either one. Okay. Questions on that one? Okay, so the one thing that makes these easier, because there's only so many ways they can look. For us, the parameter we're working with will always either be mu or p, because those are the only two that we've dealt with. We're not going to add any at this point. Okay, so the parameter will always be mu or p. On the alternative hypothesis, we really only have 3 choices for the symbol that goes in there. It's either less than, greater than, or not equal to. And then the null hypothesis is always the opposite of the alternative, and it always has to have equality with it. So it's always either greater than or equal to, less than or equal to, or equal to. Okay. So there's only so many ways I can really look. So that helps. Okay. So no question on that so far? Okay. All right, so the idea, so let's just kind of discuss the middle a little bit after we get our hypotheses, and then we're not going into detail yet, okay? But the idea, we get our hypotheses. Okay? We start off assuming the null hypothesis is true. Okay? That's the way we work through this. Okay? We'll come back to that slide. Okay? Then we would collect data and use our data to calculate something called a test statistic. And that number, that test statistic, is what we end up using to make our decision about the null hypothesis. So we start off assuming the null hypothesis is true, and then either we're going to agree or disagree, that's what we'll say for now, with our initial assumption. The way we make that decision is whether or not our test statistic is what we'll call statistically significant. And what that means is okay, remember we start off assuming the null hypothesis is true. So if we get some number that would make the null hypothesis seem not like it was true, okay? So we get some kind of unexpected number assuming the null hypothesis is true, and then that's what we end up calling a statistically significant test statistic. So let's see if we can think about that for a second. So, all right, I'm going to make a claim that we're using as our null hypothesis. Okay, so my null hypothesis might be that the average age of students at JSU is 80 years old. Okay. So I'd start off assuming that was true, and then I would collect some data, and so collect all your ages, okay, and figure out what the mean of that was. So if I got like 22 or something like that as the mean of my sample data, I would say, wait a minute, that 22 is really far away from my assumption of 80. Okay. So maybe my null hypothesis, maybe my assumption was not true. Okay. That's the idea of what's going on here. On the other hand, if I collected data, okay, and so I assumed the average age was 80, I collected data and I get like an average age of 78 in my data, then, well, that's not really far away from my hypothesis, so maybe the null hypothesis is true. Okay? That's the idea. We're being more formal about it. Okay, we're putting numbers on things. How far away does it have to be before we call it statistically significant? We'll deal with all that. That's the idea. How far away it has to be, that's what we call our level of significance. Okay? And we've briefly seen that symbol before. It's the Greek letter alpha. It's where we get our lowercase a, so it looks similar. When I draw mine, it looks more like a fish. So that's my alpha. And that's what we call level of significance. Okay. Again, that's just some number. We just give it a name and a symbol because of what it represents. Okay. And we have a relationship down here. It says alpha equals 1 minus c. What that's going back to is that picture we drew, right, where we've got a curve. Right? Confidence is the area in the middle of the curve, and then alpha is the area in the tails. Okay? Remember that? So 1 minus the area in the middle would be the area in the tails. Right? So significance is the area out in the tails. Okay? Questions? Any of that so far? Again, I know when we just have definitions, it's kind of confusing, so we'll work it out. That's for next time. Okay, we'll get more into that stuff. That's kind of what's going on in the middle. And then as we get to the end of a hypothesis test, so we've collected data, we've calculated a test statistic, we've looked to see if our test stat is statistically significant by comparing it to our level of significance, all that good stuff. And remember, at the beginning of our hypothesis test, and through the whole process really, we assume that the null hypothesis is true. Okay. And then at the end of our hypothesis test, once we have our numbers we get from our data, we have only 2 possible conclusions we can make. Okay. So there are only 2 possibilities for how any hypothesis test turns out. Okay. So the 2 possibilities or we either reject the null hypothesis. So that's the case where it looks like our data supports the alternative hypothesis. So we would reject the null hypothesis that we were assuming to be true, or we would fail to reject the null hypothesis. So in that case, we don't have strong enough evidence in our data to suggest that the null hypothesis may not be true. So we just fail to reject the null hypothesis. Really, we're just not doing much in that case. Okay? These two are not equal. Okay? These two outcomes are not equal. So if we reject the null hypothesis, okay, that's a very strong statement. Okay? Very strong statement. We're saying we have overwhelming evidence in support of our alternative hypothesis. So we are rejecting the null hypothesis that we were assuming to be true. Okay. If we fail to reject the null hypothesis, that's a very weak statement. We're really not saying much when we fail to reject the null hypothesis. All we're saying is, based on our data, we can't reject the null hypothesis. Okay. Not enough evidence there for us to reject the null hypothesis. So to try to drive home the difference, okay, and the weight of these things, okay, rejecting the null hypothesis, I compare to looking someone in the eye and calling them a liar. I mean, that's serious, right? And then failing to reject the null hypothesis is like somebody asking you a question and you're not real sure and say, yeah, I don't know. Not a big deal, right? You're just not sure. So really strong when we reject, really weak when we fail to reject. Questions on the two conclusions? Those are the only two conclusions we can have. Okay? And notice both of them have to do with the null hypothesis. So we either reject the null hypothesis or fail to reject the null hypothesis. We don't have any other options. We can't accept the null hypothesis. We can't prove the null hypothesis. We can't do anything to the alternative hypothesis. Okay? So this process, we're never 100% certain. Okay? We're not proving anything either way. What we are going to be able to say is we're 99% certain. Okay? But there's always a chance one way or another that we're incorrect. Okay? We'll get into that more also. Okay? All right, so let's try to interpret some conclusions. Okay, we'll get the setup for a hypothesis test and be given the conclusion. So either we reject the null hypothesis or fail to reject the null hypothesis. We want to interpret what that means in context. Okay. So let's look at one here. Okay. This one says, the campaign manager for a gubernatorial candidate believes that her candidate connects with a younger audience and will connect with a younger audience and will, we got some typos in here, and will draw a larger voter turnout for the 18 to 24-year-old demographic. Historically, only 25% of eligible voters between 18 and 24 years old vote in the election. A hypothesis test with a 5% level of significance is performed on the manager's claim. The result is to reject the null hypothesis. Does this conclusion support the manager's claim? Okay. So all we're trying to do, we're trying to interpret. We got a lot of information we don't need in here. Okay. All we're trying to interpret, we know that the conclusion to the hypothesis test is that we reject the null hypothesis. All we want to know is, does that support the campaign manager's claim or not? Okay. So in order to get there, we need the hypotheses. We need to know what our two hypotheses would be for this hypothesis test. So first we need to pick out the claim that the campaign manager is testing. Okay. So the campaign manager thinks that they're going to have a larger voter turnout for 18 to 24-year-olds. Okay. Historically, it was 25%. So if we have a larger turnout than 25%, that would mean that in this case, our proportion, because we're dealing with percentages, right? That our proportion would be what? Greater than 25%, right? So if we have a larger proportion of people turn out in that age range, it would be greater than 25%. Right? So that's our alternative hypothesis here. That's what the campaign manager is testing, that the proportion greater than 25% or 0.25. So the null hypothesis, what would it have to be? Yeah, it would be that P is less than or equal to 25% or 0.25. So those are the hypotheses that we would be using in this hypothesis test. It's harder, a little bit harder to pick them out when they're so wordy like this one. It takes a little extra practice to be able to sort through all that mess. But there are our hypotheses. Now we're told what the conclusion is. Okay, the conclusion to the hypothesis test, based on the data that we can't see, okay, was that the null hypothesis was rejected. Okay, so wrong way, sorry. So the conclusion was that the null hypothesis was rejected. Okay. The alternative hypothesis was the campaign manager's claim. So does our conclusion support the campaign manager's claim? Yeah. So what's happening is we've started off assuming the null hypothesis was true, but based on the data, we've rejected the null hypothesis. So that means we have overwhelming support in favor of the alternative hypothesis, which was the campaign manager's claim. So when we reject the null hypothesis, that means that the alternative hypothesis is supported by the data. Okay, so that's support. Sorry, I picked yellow. I just randomly picked one and got the worst possible color, other than white, I guess. Okay, so when we reject the null hypothesis, that means we have strong support, strong evidence in our data in support of the alternative hypothesis. In this case, the alternative hypothesis was the campaign manager's claim. So yes, this outcome supports the campaign manager's claim. Okay, another one here. Same idea on this one, we just have a different situation. Okay. It says, based on historical data, the Board of Education for one large school district believes that the percentage of high school sophomores considering dropping out of school is at least 10%. A high school counselor in the district claims that this percentage is too high. A hypothesis test with alpha of 0.02 is performed on the counselor's claim. The result is to fail to reject the null hypothesis. Do the findings support the counselor's claim? Okay. So we want to know if the counselor's claim is supported. We need our hypotheses. Okay. So what's the counselor claiming? Says the high school counselor claims that this percentage is too high. So what percentage is it talking about? The 10%. So if the counselor thinks that 10% is too high, what's the counselor claiming about the percentage that it's less than 10%? Less than 10%. So I accidentally put my blank slide the wrong direction here, sorry. For our alternative hypothesis, the counselor's claim here is that percentage of students thinking about dropping out is less than 10% or 0.1. The null hypothesis would be what was stated as historically, right? That the percentage is greater than or equal to 10%. So on that one, we could have potentially come up with a null hypothesis first and it would have been fine. Okay, because we could have seen this part first. Okay, it says, based on historical data, the Board of Education believes that the percentage is at least 10%. That would be greater than or equal to 10%. And that's okay if that's the one you see first. You just got to realize that since it's greater than or equal to, if it has equality with it, that would be the null hypothesis. Okay? So if you see that one first, that's okay. Usually alternatives easier to come up with first, but it doesn't matter which one you get first. As long as they end up being opposites and you have equality with the null hypothesis, you're in good shape. Okay, so we've got our hypotheses. Now this says the result is to fail to reject the null hypothesis. So our null hypothesis here, this one is not rejected. So does that support the counselor's claim? The counselor's claim was that the percentage was too high or that it was less than 10%. But based on our data, we could not reject our null hypothesis. So does that support the counselor's claim? No. If we couldn't reject the null hypothesis, we don't have support for the alternative hypothesis, or at least not enough to reject the null hypothesis. So here, when we don't reject the null hypothesis and the alternative hypothesis is not supported by the data, okay. Now here's something you have to be a little careful about. Does that mean the high school counselor was wrong? No. Okay. Remember, if we fail to reject the null hypothesis, that's a very weak statement. A very weak statement. The strongest statement we can make, okay, when we fail to reject the null hypothesis is that there was not enough evidence in our data to support the alternative hypothesis. Okay. That's all we can say. Counselor may be right. He may have just got bad data. Maybe he needs to go back and collect some more data. Okay. It's very, very weak statement when we fail to reject the null hypothesis. Okay. We're not saying anybody's right or wrong. Okay. It's not. All we can say is that we did not have enough evidence to reject the null hypothesis. That's it. Questions on that one? So if you reject the null hypothesis, that means we have strong evidence in support of the alternative hypothesis. If we fail to reject the null hypothesis, that means we didn't have enough evidence to support the alternative hypothesis. Okay. Rejecting the null hypothesis is a very strong statement. Failing to reject the null hypothesis is a very weak statement. Okay. No questions? Okay, so that's the beginning and the end, okay, of doing a hypothesis test. We get our hypotheses, go through all that stuff in the middle, and at the end we come up with our conclusion. We either reject or fail to reject the null hypothesis, and then we've kind of seen how it plays out. What does that mean about our claims we're making? Okay, where they're either supported or not supported by the data. Okay. Doing this process, remember I said that we're never proving one hypothesis or the other with absolute certainty. And what we're doing is we're attaching some type of percentage, kind of like we did with confidence intervals, right? Where we can be a certain percent confident in our result. Okay? We can say that we're supporting our alternative hypothesis at a certain significance level. This is the way that that gets worded a lot. But remember, significance and confidence are related. Okay? There's a formula that relates the two together. So with that said, since we're never 100% certain with a hypothesis test, that means that we can do everything in a hypothesis test perfectly correct and end up with the wrong result. That's a possibility. So those times when that happens, we call those two situations errors. Okay. And we have two different types of those. Okay, two different types of those. So when we, where'd it go? Yeah, there we go. When we say we've committed an error in hypothesis testing, we're not saying we've made a mistake. It's just inherently built into this decision-making process that sometimes we're going to be wrong, okay? Because it's not 100% airtight, okay? And we can't make it 100%. Okay, we'll talk about that in a second. So there's always the possibility of making one of these two types of errors. Okay? So the first thing that can go wrong, okay, is that our null hypothesis is really true in reality, but based on the data we collect and how we go through the hypothesis testing procedure, we end up rejecting the null hypothesis anyway. Okay? So that's not what we want to happen, right? If the null hypothesis is true, we don't want to reject it. So when that happens, when we reject a true null hypothesis, that's an error. Okay? The other thing that can happen is that our null hypothesis is actually false, okay? But we don't get strong enough evidence in our data to reject it. So we want to reject a false null hypothesis, okay? But if our evidence is not strong enough, sometimes we may fail to reject the null hypothesis even though it's false. Okay? That's false. So this one, when we reject a true null hypothesis, we call a type 1 error. And this one, when we fail to reject a false null hypothesis, we call a type 2 error. Here's a little picture there. Okay? So if the null hypothesis is true and we reject it, that's type 1 error. If the null hypothesis is false and we fail to reject that, that's a type 2 error. So what we want to happen is we want to reject a false null hypothesis and we want to fail to reject a true null hypothesis, right? Those are the two things we want to happen. Okay. All right. Unfortunately, okay, we can't eliminate these errors, okay, with the way this is set up. So what we try to do instead is we try to minimize the potential for the errors to happen. But the problem with that is that if we minimize the potential for one type of error to happen, that increases the potential for the other type of error to happen. So if we decrease the chance of a type 1, we increase the chance of a type 2. And if we decrease the chance of a type 2, we increase the chance of a type 1. Okay? So in practice, what ends up happening is we're forced to choose which one of these is worse. Okay? Is it worse if we reject a true null hypothesis, or is it worse if we fail to reject a false null hypothesis? Okay? And that's different. Okay? The decision there is different depending on the context of where you're doing the hypothesis test. Okay? Most of the time in academics and most of the fields that all the majors that take this class are in, most of the time what we end up doing is we minimize type 1 error at the expense of increasing type 2 error. Okay? But there are situations where you want to do the opposite, different fields where you're working in. Okay, so let me give you an example of a real life thing that works the same way. Okay, where we have the two types of error and we can't get rid of either one, and we have to pick which one to minimize. Okay, we have at least in theory, okay, I'm not making any bold claims here or anything, but we have a decision-making process that's supposed to be similar, and in theory it is, and that is our criminal court system. It's our criminal court system. So either null hypothesis is true or the null hypothesis is false. And then we've got we either reject the null hypothesis or we fail to reject the null hypothesis. Right? Okay, so let's think about our court system. So what's the assumption that's supposed to, okay, in theory, okay, what's the assumption that's supposed to be made when a trial starts? The person's supposed to be assumed to be innocent until proven guilty, okay? So our null hypothesis, okay, is that the person is supposed to be innocent. It's what we're trying to assume, what we're supposed to assume, right? So if HO is true, that would mean our person is innocent. If HO is false, that would mean our person is guilty. Okay? In reality, right? And then what are the two verdicts that can be handed down? We either say a person is, we say they're guilty if we reject the null hypothesis, or what's our other verdict? Not guilty, okay, not guilty. So set up the same way. Have you ever noticed that we say guilty or not guilty or innocent? Because we don't call them innocent because we cannot prove the null hypothesis set up this way. Okay. So what are the things we want to happen here? If a person is guilty, we want them to be called guilty, at least by design. And if a person is innocent, we want them to be called not guilty. So those would be the two correct situations, right? What's supposed to happen. But we always have a risk because we can't be 100% certain. Right? So we always have a risk of these two situations. So which one's type 1, which one's type 2? So if we reject a true null hypothesis, that's a, do you remember which one that is? That's a type 1 error. That's type 1. So here in this box, that's what we would call a type 1, and we use Roman numerals, so type 1 error. If we have a guilty person and we don't reject that false null hypothesis, that's a type 2 error, type 2. So there's always a chance of these two things happening. We have to think about which one's worse. And we minimize the one that we think is worse. So and this is an opinion question. Okay, so what do you think is worse? Okay, do you think it's worse to convict an innocent person or to let a guilty person go free? That's what we would have to decide. Okay? And that's a personality thing. Okay, from person to person, you get varied answers there. Typically, you're probably in the majority if which one you think's worse. Anybody want to put yours out there? Think it's worse to convict an innocent person or let a guilty person go free? All right, so we got a mix. Okay. Typically, okay, the majority of people tend to gravitate toward the idea that it's worse to convict an innocent person. Okay? And the way our court system's supposed to be designed, at least, okay, that's the one that we try to minimize. Okay? Right, we're supposed to have evidence beyond a shadow of a doubt, convict, and I know all that, you get the real world thrown in and all that stuff doesn't work the way it necessarily is supposed to, but that's by design, in theory, the way that our court system is supposed to work is to minimize type 1 error, okay, at the risk of letting some more guilty people go free. Okay? So here, if our evidence is not strong enough, then the guilty person goes free. Right? And so those are two types of errors. So in that case, probably the majority of people would say minimize type 1 at the risk of type 2. And again, it's personality based, but that's the thought there. Okay, but let's think of a situation where we would want the opposite. Okay, so let's think about we're working quality control on parts that go on passenger airline airplanes. Okay? We're making parts for passenger jets. I got hundreds of people flying on these things. So we're doing quality control. So a type 1 error there would be that we have a good part that we throw away. We throw away a good part. That's a type 1 error. A type 2 error would be that we have a faulty part that we let pass inspection. Okay? So in that case, type 2 would be worse because we don't want to take a bunch of crappy parts and say they're good and put them on all of our airplanes. Okay? It's a lot better for us if we, every once in a while, we have a good part that we throw in the garbage instead of crashing airplanes and killing a bunch of people. So in that case, we would want to minimize type 2 error at the risk of maximizing type 1 error. Okay? So it's context-based. Okay? For us in this class, in most of academics and in most of the fields where most of the majors in this class end up working, we minimize type 1 at the risk of increasing type 2. Okay? So for us, we think it's worse to call somebody a liar, right? They've published some number and then we say, no, that's not right. Based on the data, you're wrong. We think that's worse than just saying, we're not real sure. Okay, so you can think about it that way too. And I said, rejecting the null hypothesis, that's when you look somebody in the eye and call them a liar. It's bad if you're wrong in that case. Okay? If you just say, I'm not real sure, then it's not that big a deal if you're wrong. That's where we're at. Okay. Does that make a little bit of sense at least? Okay. Kind of hard to wrap your head around to start with. You just, you have natural thoughts like, well, we don't want any type of error. Okay, well, that's true. We could, all right, let's talk about that. Why can we not just get rid of one of the types of error? Let's think about it in the situation of court. Okay, because that's at least the idea. You watch crime shows. Okay, at least that's, the idea is there. So if we completely eliminated type 1 error, how could we do that? We would want to make sure that we 100% absolute certain never convicted an innocent person of a crime. The only way we could be absolute certain that we never convict an innocent person of a crime is to never convict anybody of a crime, right? And then if that's the case, if you never convict anybody, court system's not a whole lot of use, right? We just don't need one. Okay? Type 2 error, if we want to 100% eliminate it, we absolutely, without any doubt, absolute certainty, never let a guilty person go free. And a person that's charged with a crime, never let a guilty person charged with a crime go free. How can we do that? Everybody that ever gets charged with a crime is guilty. Okay? Again, then the court system is not very useful. Not very useful. So you don't need it. Just charge them with a crime, throw them in jail. Okay? So we don't want either one of those situations. Okay? So we're stuck with having to deal with these two. So we're having to deal with those. Questions? All right, so real quick, this last part short. Okay. Let's pick out, let's look at the conclusions of some hypothesis test and pick out, did we make the right decision or was it an error? Okay, now, let me say this, in real life, we normally don't ever know if we've made one of these two. Okay. Because if we already knew the real value of the null hypothesis, we wouldn't be having to do a hypothesis test. So usually we're trying to figure out what this value is. Okay. So when we get finished, we don't have any way of verifying if we were right, made a correct decision, or if it was an error. So every time we end up with a conclusion that we reject the null hypothesis, we always have to keep in our mind that there's a possibility that that result was a type 1 error. And the same thing, every time we fail to reject the null hypothesis, we have to keep in our mind that there's a possibility that our result was a type 2 error. Okay? Always has to be there. Okay? All right, so let's look at this one. So it says a television executive believes that 99% of households in the United States have at least one television. An intern at the executive's company is given the task of using a hypothesis test to determine whether the percentage is actually less than 99%. The hypothesis test is completed, and based on the sample collected, the intern decides to fail to reject the null hypothesis. Hey, let's stop right there for right now and get our hypotheses set up. We need to know those. So our alternative hypothesis, the one we're testing, is that the percentage of people that own televisions is less than 99%, or that P is less than 0.99. Did I leave myself some room? I didn't leave myself some room here. Sorry. That's the alternative hypothesis. Okay. The null hypothesis then, I'm going to write it over to the left, sorry about that. It'd be that P is greater than or equal to 0.99. Okay. And then we have the decision. The decision, we failed to reject the null hypothesis, so the null is not rejected. Okay. But then the last sentence says, if in reality, 96.7% of households own a television, was an error made. So our null hypothesis says that P is greater than or equal to 99%. This is the real number. So was the null hypothesis really true or false? It was false because it says it's bigger or the same as 99%, but the real number is 96.7%. So here the null hypothesis was false, but we failed to reject the null hypothesis. So is that an error? So here HO was false. But HO is not rejected. So we failed to reject a false null hypothesis. So is that an error? It is an error. Which one, type 1 or type 2? Type 2, type 2. So this is a type 2 error. Type 2 error. But again, remember, if we already know this number in real life, right? In real life, if we know this number, we're not going to be doing a hypothesis test. That makes a hypothesis test pointless. We can just say this is the real number. So in real life, we would not know for sure if we'd made an error. Let's do one more. All right, this one says, let's keep going. This one says, insurance companies commonly use 1,000 miles as the mean number of miles a car is driven per month. One insurance company claims that due to our more mobile society, the mean is more than 1,000 miles per month. So there's our alternative hypothesis, and that the mean is greater than 1,000. So our null hypothesis would be that the mean is less than or equal to 1,000. The insurance company tests its claim with a hypothesis test and decides to reject the null hypothesis. So here's our null hypothesis, that the mean is less than or equal to 1,000. And we have rejected this. Okay. And then it says, assume that in reality the mean number is 1250. Was that an error? So our null hypothesis says the mean is less than or equal to 1,000. That's false because the real number was 1250. So our null hypothesis was false. Our conclusion was to reject the null hypothesis. So we've rejected a false null hypothesis. Is that an error? That's what we want to happen. If the null hypothesis is false, we want to reject it. So this one's not an error, and this one is a correct decision. I said that was the last one. We got one more, I'm sorry. We'll go through it quick. Last one. Okay, we got a report that children watch a mean of 4 hours of television per night. Kiko believes the number of hours children in her neighborhood watch television is not 4. So her alternative hypothesis here is that the mean is not 4. So that would be that the mean is not equal to 4. Okay. So our null hypothesis would be that the mean is equal to 4. Okay. So here's our null hypothesis that the mean equals 4. Okay. So she performs a hypothesis test and rejects the null hypothesis. Okay, so this is rejected. Assume in reality, children in her neighborhood do watch a mean of 4 hours. So if children actually do watch 4 hours of television on average, our null hypothesis was that the mean is 4. It means our null hypothesis was true, right? Because it had the right number. But the result of our hypothesis test was to reject the null hypothesis. So if we reject a true null hypothesis, that's a type 1 error. Type 1 error. So rejecting a true null hypothesis, that's a type 1 error. Okay. Questions there? There's only like 1, maybe 2, where you're picking out if it's an error or not in the assignment. Most of the assignment is just stating the hypotheses. Okay, so practice, practice, practice on those. Okay, the best thing you can do for getting the rest of chapter 10 is to work on 10.1 until they're easy to get the hypotheses. Because we don't want to have to spend a lot of brain power on getting the hypotheses when we start doing all the other stuff. Okay, so if you can, between now and Thursday, if you can get down getting the hypotheses pretty good, you'll be in good shape. Okay. All right, so if you didn't get on the sign-in sheet, get on there before you leave.
We don't have an assignment due until Thursday, right? Because I didn't get a notification.
Yeah, maybe not even Thursday. It might be next Tuesday for this one.
Okay.
Yeah. Yeah. Okay. If you need some candy on the way out, and get some out of the bowl. Need one for the road.